Good morning everyone, this is Preeti Devi of Indian School Mulladda. Today our topic to study is electric potential. Do you guys know what is electric potential? Electric potential is the work done by the source charge to bring a unit positive test charge from infinity to a point. Okay, let us suppose take a source charge Q. Okay, now and take a point P. Now the work we do to bring a unit positive charge from infinity to this point, that is called electric potential. Okay, electric potential for a single charge V is equals to KQ by R, where R is the distance from the source charge to the point. Q is the K is the Coulomb's constant, which is equal to 9 into 10 to the power 9 Newton meter square per Coulomb square, and Q is the source charge. Do not mix up electric potential and electric field. For electric field it is KQ by R square, but for electric potential it is KQ by R. Okay. Now, when we study electric potential, we have some cases to discuss, such as now let us consider a dipole. Let us consider a dipole of length 2a, consisting of two equal and opposite charges, plus q and minus q. This is a dipole. Now, electric potential for a dipole at the axial point. Axial point means the point on this line. It can be on the dipole, it can be outside the dipole. The electric potential for such a point, it is 1 by 4 pi epsilon 0 P by R square. Electric potential for an equatorial point is 0. Why? Because electric potential by this charge is cancelled by electric potential at this charge. Okay? And today what we are going to study briefly is electric potential at a general point. Now, let us consider a point P somewhere. It's not an equatorial point, it's not an axial point, anywhere in the space. Okay. It is at a distance r from the center of the dipole. We are taking it from the center of the dipole, okay? And the angle between r and electric dipole is theta. Okay? Now, the distance between A and P is r1, and from P to B is r2. Okay? Now, let us take electric potential at P due to the source charge A, which we can write it as VPA is equals to minus KQ by R. Now, you might be wondering, why did we take a sign? We took sign because electric potential is a scalar quantity. We need to consider its sign. Okay, everyone? Now, electric potential at point P due to the source charge B, which is equals to KQ by R. This is R1, this is R2. Why did we take R1 and R2? Because R is the distance from the point charge to the source charge. Okay? Now, to get the total electric potential at point P, we need to add them. Why? According to superposition principle. Okay? So, total electric potential at P due is VPA plus VPB, which is equals to minus KQ by R1 plus KQ by R2. Now, we can take K common because it's a Coulomb's constant and constants does not vary, right? And we can take Q common. Why? Because for a dipole, it is two equal and opposite charges. Okay? So, it becomes KQ by R2 minus R1. Okay? Now, we need to cross multiply, which will then be this equation, then it becomes Now, this is the equation for a general equation for a dipole, okay? Now, let us consider what if the dipole is a short dipole, okay? When we consider it as a short dipole, this equation then becomes kq by now you all guys will have a question. How did this become this all of a sudden? Okay, for a dipole, since it's a very short dipole, this theta will be approximately equal to this theta, right? So since it's approximately equal, we take it as equal only. Okay, then this becomes theta. This and this is equal. Okay, now let us consider a perpendicular form here. When we take perpendicular, this r and this r becomes equal. Am I right? Because since one side was long, we took a perpendicular, then this becomes an equilateral triangle. So we can say that it's an equal. And then this side becomes r1 minus r2. Okay. Now when we take cos theta for this angle, which is cos theta is equals to adjacent by hypotenuse. This is adjacent, this is hypotenuse, okay, which cos theta becomes r1 minus r2 by 2a. Okay. Now when we rearrange this equation for r1 minus r2, it becomes 2a cos theta, which we apply here. Now I told you that it's a very short dipole. So we can say that since it's a very short dipole, r1, r2 becomes here also approximately, right, equal. So we use as r only. That's why we are taking r1 into r2 is equals to r square. Now you might be also wondering, since it's a very short dipole, very small angle, very small r, why don't we take it as 0 itself? Easy, right? Khatam khalas case. But we can't. Why? Because if we take it as 0, we won't have any information for the equation. Like we don't know what is dipole for, or what is electric potential for any point. It's 0? No, it's not 0. We cannot take it as 0 because no information, nothing is there then. Okay? So this we got the equation. Now we can write this equation in vector form, which then becomes kq. For a dipole moment is equals to 2aq. We remember, right? We studied it back. Then we can write r cap by r square. Okay? This is vector form. Now you might see here r cap is 1. Cos theta is as dot product. So that's why it becomes k p dot r cap by r square. This becomes p. Cos theta is dot product. R cap is 1. So it doesn't affect the original formula. Okay. We can also write this equation in the form how did this happen? When we multiply the numerator and denominator by r, we will get this equation. Okay. Now, when we study physics, there are always exceptional cases or special cases everywhere around. So let us see some, special cases that we need to discuss. Now, what if theta is equals to 0? When we use this equation, if theta is equal to 0, it becomes an axial point. Am I right? So axial point electric potential is 1 by 4 pi epsilon 0 p by r square. Okay? And for if theta is equal to 90 degree means it becomes an equatorial point. This charge gets cancelled by this charge. Then it's a 0. Am I right? And here we come to the end. Does anyone have any queries?
Questions, please.
Yes.
So this equation again, is it going to be universally valid in all cases?
It might be valid to most of the cases, but not all.
So can you emphasize on the conditions where they will not be valid?
Mostly it's valid to everything. I'm not sure about which cases it's not valid. I'll get back to you later for that.
In case these charges, they are not stationary, then will it be valid?
We are considering stationary charges.
No, yeah, that's what I'm asking.
No, it won't be valid then.
Yeah.
Because if it's stationary charges, means the charges will keep on changing. So if the charges are keep on changing, we cannot take the case only itself. We have alternatives then.
So it's not universally valid.
It's not universal. But it has like conditions. Only for stationary charges you can use these terms, because for a dipole, charges are stationary. Any else? Yeah.
You can see birds that sit on, maybe sitting on the wires that carry current,
Yeah.
but they don't get the electric shock.
It's because
Is the concept of potential applied there? Could you answer this?
the thing is, for the wires, they have insulatings. Above the wire, there are insulating covers, so electric current doesn't flow out. That's why they don't get electric shock. It doesn't have any relation here. Anything else?
So,
Yes.
like in such a case, there's this dipole, right?
Yeah.
So, like, if we assume that they are not of equal magnitude, let's just say they're not assuming it. So, where will be the point of zero electric field in this case?
Can you repeat your question, please?
So, let's assume that these are not of equal magnitudes.
Okay.
So, where will there be zero electric field in this case?
See, first of all, dipole means an equal and opposite charges should be there. Okay, your question. Second thing, if it's changed.
Yeah, they're not of, they're not of equal magnitudes. That means
Yeah.
the value is not same.
Yeah. Then we have different cases. We have superposition. Different, for two charges, we have different cases. Superposition, like electric potential for 2 points, for 3 points, for 3 source charges, it's there.
So, allow me to rephrase my question. So, will it be lying between those two charges or will it be lying outside?
It depends. It depends on the value of R. Depends
so
on.
So you're telling that it might be zero between the two charges.
Yes.
How will it be zero between the two charges? It's negative and positive. So
Yeah.
if you consider the vectors, can it ever be zero at any point?
See, if your question is like, see, for an electric potential, you're saying if the magnitudes are changed. You're saying the magnitudes are changed and the point P is between.
No, it's okay. Even if the magnitude is changed or not, can it ever be zero between the negative and positive?
For an axial line, no.
Yeah,
No.
That's what I thought.
Because for an axial point, see, if it's in the center, exact center, then it might be zero. It is zero then.
It cannot
But
be zero.
no, if it's in the center, means A, and you have a center point for a dipole, right? If it's in the center, on the center point, yes, it is zero. Other anywhere, it's not zero. Because it comes into equatorial point then. You getting me?
Can you explain diagonality? So that
Yeah, why not? Surely. Let us consider this. Okay. Here, charges minus Q and plus Q. Now you're saying that the point P is in the center. Yes?
anywhere, I never said center, anywhere between.
If it's anywhere, then it is not zero. If it's only on the center, it's zero.
If it's in the center, it's zero.
Yeah.
But it's a general principle that for a dipole, the electric field cannot be zero at any point between the two charges.
Because if it's in
No,
the
it's a general principle. I don't know, someone said that, but it's a general principle. Right?
I'm not sure about those stuff. But then what I know according to my knowledge, because I'm not a genius at all here, very average student here.
Okay, let's
But
just try to understand the concept here. Right? So for plus Q charges, the electric fields will always be away from each other.
Yeah.
And for minus Q, it will always be coming towards it, right?
Yeah.
So can you try to represent that? Then we'll see if it's actually going to be coming to you.
I don't get a question.
So for minus Q charge, the electric field is always going to be coming towards it. Am I right?
Yeah. The point charges.
Yeah. So just draw an arrow over there.
Like this? No, you
It's
mean.
coming towards it, right? So how's it going up there? Let's just draw an arrow.
Here we are considering positive charge. That's why we're saying dipole is from negative to positive.
Yeah, but the question was, it's going to be, no, I'm just telling you. So
Yeah.
let's just draw an arrow over there. So it's right. Yeah, so for plus charge, again it's going to be going away from it. It follows the same direction, right?
Yeah.
So how will it be zero? If you, by the vector addition, we are going to be, or let's say superposition also, we're going to be adding
Let
both
me
of
say
them.
the
How will
answer,
it be
no?
zero?
Okay.
What is the answer? Do you know that?
Your answer.
So it's never going to be zero.
Is it about electric field or potential?
Electric field.
Electric field. Mine is electric potential.
But you're also covering the topic of electric field.
No, I just gave a general idea that
targeting just general.
No, I just gave you an idea that there is a confusion between electric field and electric potential in the starting of the introduction. The formula, it's very same, just a R square difference that we make a mistake every now and then. I just gave a brief idea that my topic is not electric field, okay? I'm so sorry, but I'll get back to you with the answer soon.
Okay.